In part 3 of this 3-part video series on simple linear regression, we'll deepen our numerical summaries to include statistical models. In our penguin example, we observed a positive linear relationship of body mass with flipper length. The line drawn here represents the simple linear regression model of this relationship. In general, models are simplified representations of reality. For example, an architectural model of a house captures the key features of an actual house, but is not the house itself, thus cannot capture every detail. Similarly, this statistical model is a simplified representation of the relationship between body mass and flipper length. The actual more nuanced relationship is not actually dictated by a line. Further, in comparison to the scatterplot visualization of this relationship, this model can be used to more accurately describe the relationship. For example, the rate at which penguin body mass increases with flipper length. And it can be used to more accurately predict body mass from a given flipper length. To utilize the simple linear regression model, we need to obtain the model formula. First, let y represent the body mass response variable, and x represent the flipper length predictor variable. Then the formula for the simple linear regression model drawn here is as follows. Let's focus on the new notation at the left-hand side of the equation. Here, E represents an expected value, or average. And inside the square brackets, we have y given x. Putting this together, the left-hand side of the equation is read as the expected or average value of y given x, or in our penguin context, the average body mass at a given flipper length. Further, note that the right-hand side of this equation, negative 5.78 plus 0.5x, is the formula for a line. That is, we can rewrite it in the form of a plus bx. To better understand our model formula, let's apply it to an example. Suppose we observe a penguin with a flipper length x of 18 centimeters. We can then calculate the expected body mass y given this flipper length by plugging in 18 for x in our model equation. The outcome is 3.22 kilograms. Putting this together, if a penguin has 18 centimeter long flippers, we'd predict or expect it to weigh 3.22 kilograms. That is, this would be the average or typical outcome. But predictions aren't perfect. For example, suppose we go on to observe a penguin with a flipper length of x equals 18 centimeters, but a body mass of y equals 4 kilograms. This observation is represented by the big black dot here. And notice that this penguin falls above the trend line. Specifically, its body mass is bigger than our prediction of 3.22 kilograms, represented by the red dot. The residual, represented by the red line, captures the difference between what we observed and what we predicted. That is, it captures our prediction error. Specifically, the difference between the observed y value of 4 kilograms and the expected or predicted y value of 3.22 kilograms is 0.78 kilograms. Stated in context, the penguin's observed weight was 0.78 kilograms greater than what we expected based on its flipper length. Beyond using a model for predictions, the formula also provides important insight into the relationship of interest. First, let's consider the first number in the formula, the intercept coefficient, negative 5.78. This value can have physical, statistical, and contextual interpretations. Physically speaking, the intercept indicates where the line crosses the y-axis. It's the y-intercept. But the y-axis isn't shown in the plot here. So let's zoom out. The red circle here now represents the y-intercept. At the y-axis, when x equals 0, y equals negative 5.78. Connecting this back to our statistical setting, the intercept indicates the expected or average value of y when x is 0. that is, plugging x equals 0 into our model formula, the resulting expected value of y is negative 5.78. In some examples, the intercept can also hold contextual meaning. For example, translating the x's and y's in our statistical statement to our penguin context, we might say, we expect a penguin with 0 centimeter flippers to weigh negative 5.78 kilograms. But that's silly. It doesn't make sense to have 0 centimeter flippers, nor does it make sense to have negative body mass. In this example, we did not observe penguins with flipper lengths or x values near 0, so we can't interpret the intercept in context. More generally speaking, we shouldn't extrapolate our model far beyond the range of our observed data. Let's move on to the flipper length coefficient of 0.5. Again, this has physical, statistical, and contextual meanings. Physically, the flipper length coefficient indicates the slope of the line, or the rate of change in y relative to x. In previous classes, you might have thought of the slope as rise over run. For example, when we increase x by 1 unit, from 18 to 19 centimeters, the expected y outcome increases by 0.5 units. Similarly, when we increase x by 1 unit from 21 to 22 centimeters, the expected y outcome increases by 0.5 units. Connecting this back to our statistical setting, the slope measures the change in the expected or average value of y associated with a 1 unit increase in x. For example, when x equals 18, we expect y to be 3.22. Now, if we increase x by 1 unit from 18 to 19, and then plug 19 into our model formula, then we expect y to be 3.72. That is, when we increase x by 1 unit here, the expected outcome of y increases by 0.5, the value of our slope. Finally, translating our x's and y's to the penguin context, we conclude that a 1 centimeter increase in flipper length is associated with a 0.5 kilogram increase in average body mass. Our final contextual statement here demonstrates some important details when interpreting coefficients. First, it's important to include units. Our interpretation makes clear that we're measuring flipper lengths in centimeters and body mass in kilograms. Without this context, the slope value of 0.5 really means nothing. Second, don't imply cause and effect. For example, we would not want to say something like, increasing flipper length by 1 centimeter results in a 0.5 kilogram increase in body mass. That phrasing implies a causal relationship between variables, whereas our original phrasing focuses on correlation or association. Finally, remember that models describe averages, not individuals. For example, it would be incorrect to state that if a penguin's flipper length increases by 1 centimeter, its body mass will increase by 0.5 kilograms. That phrasing implies that our model slope describes individual penguins, whereas our original phrasing makes clear that it describes expected or average behavior across penguins. The simple linear regression model is summarized here in the general, not penguin-specific setting. Notice that the intercept and x coefficients are represented by Greek letters, which we can read as beta 0 and beta 1. Though likely new to you, this is the standard notation in statistical modeling. For future reference, I've also summarized the physical, statistical, and contextual meanings of these beta coefficients here. Importantly, the notation here represents a population model. That is, a model that describes the relationship between y and x among the entire population of interest. For example, among all penguins. Since we typically don't have data on an entire population, we can't actually determine the beta 0 and beta 1 values here. That is, there's no way to know the exact model underlying an entire population. In practice then, what we do is build a sample model, which uses data from a sample to estimate the unknown population model. In our penguin example, we built a sample model using data on just 344 penguins, and this provides an estimate of what's happening in the broader population. For communication purposes, we distinguish estimates of beta 0 and beta 1 using hat notation. Basically, we put a little hat on top of quantities that have been estimated. For example, the notation here is read as beta 0 hat, and it's a sample estimate of beta 0. Finally, the formula for our sample model doesn't pop out of nowhere. It's identified using the following least squares criterion or rule. We want to choose the line that produces the smallest collection or sum of squared residuals. That is, the line that produces the least squares. Some pictures can help illustrate the point. At left is the sample model we studied earlier, and at right is an alternative that's clearly worse. Whereas our original sample model accurately describes the trend in the relationship between body mass and flipper length, the alternative model does not. What we're really comparing in these two plots are the model residuals, that is, how far the observed data points fall from the model. These residuals are represented here by red lines. Notice that the model on the left has smaller residuals, hence smaller squared residuals, than the model on the right. That is, the observed data points tend to be closer to our original model than in the alternative model. And that's a good thing. It means that our original model better captures the relationship between body mass and flipper length. In fact, in comparison to any other possible sample model, our original sample model has the smallest possible collection of squared residuals. That is, it satisfies the least squares criterion. I'm going to conclude this video with specific formulas behind the least squares criterion. Again, for the purpose of IntroStat, these formulas are optional, but if you're interested in the mathematical details behind our work or you may go on to study more statistics or other quantitative fields, I encourage you to stay on. Otherwise, please feel free to stop the video at this time. First, we have our usual sample pairs of observed y and x values. Next, let's use our hat notation to denote the sample model predictions of these n data points. For example, y hat 1 is the predicted outcome of the first data point, y1, and it's calculated by plugging the corresponding predictor value x1 into our sample model. So this gives us predictions y hat 1, y hat 2, up to y hat n, again calculated from our sample model. Next, we can calculate the residual for each data point, that is, the difference between the observed data points y and their model predictions, y hat. To understand the overall quality of the model predictions, we can sum up the squared residuals. That is, we take the squared residual for the first data point and the squared residual for the second data point, and so on, and add them up. On the left-hand side of this equation is just shorthand notation for summing up the squared residuals for I equals 1 to n. Next, recall that the least squares criterion selects the sample model coefficients, beta hat 0 and beta hat 1, that minimize the sum of squared residual. The version of this formula or statement on the right simply reiterates that our model predictions, hence our residuals, are calculated using our beta hat estimates. Finally, the least squares criterion has a solution here. That is, we can write out a formula for the beta hat 1 and beta hat 0 quantities that minimize the sum of squared residuals. Those formulas are shown here, but in practice, we'll use statistical software to calculate these for us.